So section 4.3, we're going to introduce the logarithmic function. And I'm going to start it this way. I've got two functions here. And my question for you to start is, which one of these, f of x or g of x, is an exponential function? Or are they both exponential? Or neither? Which one's the exponential function?
G.
Yeah, g of x. When you have a base to some variable exponent, that's your exponential function. So some fixed number. That number has to be greater than 0 and different than 1 to be an exponential function. And of course, it satisfies both of those. Now, let me remind you what we did a while ago when we were trying to find, say, the inverse of a function. Hopefully you remember that calculation. We started out by replacing the function by y. So y equals this. And then you interchanged x and y, right? So x equals y cubed, x equals 3 to the y. And then you solve for y. So that'd be the cube root of x equals y. And then I asked you to rewrite it as f inverse of x equals the cube root of x. And that works great for f of x, but for g of x, you're kind of stuck. It's not much that all the work we've done up till now allows you to do. And what we need to do is we need to introduce another function. And that new function that allows us to solve for y is the logarithm. It's the inverse. By definition, it's the inverse of the exponential function. So that would be log base 3 of x equals y. So that g inverse of x is log base 3 of x. That's your inverse function. And that's kind of like the beginnings of logarithms. There's a lot more to say about them. But let me kind of give you a general idea of logarithms, how to work with them. So I would write this down on the top of your test when you get it next time. So if you have a to the y equals x, that's equivalent to, so is equivalent to, let's see, it'd be log base a of x equals y. These two things are interchangeable. And what that's saying, when you take the log base a of x, you're asking, well, what power of this base, what power of a gives me x? That's the question that you're answering to yourself. So well, let me kind of add that to this little thing here. When you're taking the log of something, you're asking yourself, what power of a gives me x? And the answer is y. Just that number or that expression on the right-hand side. And so what I want to do is I want to play around with a lot of examples to get comfortable with this. And eventually we're going to graph this and look at its graph and play with its graph a little bit as well. But for starters, just know that the logarithm is the inverse of an exponential function. And that's going to have implications for the graph, its domain, its range, that kind of thing. As a reminder, when you go from a function to its inverse, the domain and the range interchange. All right, so here's a little handout that is on D2L. And let's start with the first one. Log base 2 of 16, and I already wrote that there for you, it's a 4. That's because 2 to the 4th power equals 16. And now there's some symmetry here that's really not symmetry, it's more like coincidence. But how about this? What power of 4 gives me 16? 2. Okay. Now I can rewrite that, I can write that equivalently using exponents. And the way it works is you take this to this power, so the base to this power equals this. So it's going to be 4 to the 2 power equals 16. And like I said, the coincidence stuff here is just that. It's coincidence. Let's move on down here a little bit. And the people in class here have a little bit of an advantage because on the right-hand side of the front board, I've got the first 10 perfect, first 11 perfect cubes and the first so many perfect squares. What power of 5 gives me 125? Let's see, 5 to the first power is 5. 5 to the second power is 25. 25 times 5 is 125. So it sounded like 3. Now if that's 3, then I should be able to rewrite that using exponents. What would be the equivalent expression using exponents? What to what power equals what?
5 to the third power equals 125.
5 to the third power equals 125. Perfect. Perfect. Now there's a couple more here that we can look at. What power of 9 gives you 81? What power of 4 gives you 64? What power of 3 gives you 81? What power of 7 gives you 7? So I'm going to give you a minute or so to look at those and figure out what those are. And then we'll do the big reveal. So for right now, here's my low-tech pause. So if you're at home watching this video, you can take a moment and answer these things, and then come back and check your answers. Unpause and check your answers. Try to also rewrite them using the equivalent expressions in exponents. All right. So my Zoomers can throw some numbers in the chat. Maybe throw in 1, 2, and 3, A, B, and C. And then if you get adventurous, you can also do the right-hand stuff as well. Rewrite them using exponents. Okay, cool. So let's take a look here. 9 to what power gives you 81?
Second power.
Yeah, second power. So equivalently, that's going to be 9 to the second power equals 81. 4 to the third power equals 64. 4 to the third power equals 64. How about this one? Did anyone get this one? What power of 3 gives you 81?
4.
4. Thank you. So that'd be 3 to the fourth power equals 81. Nice. These are basic ones, and if you're not that good at it, don't worry about that. At the very start of next section, I'm going to give you a formula that allows you to calculate this in, strange cases like this. Now, let's start moving into some that are going to ask us to think a little bit more. Now, this first one, I hope it is not so bad. Log base 7 of 7. What power of 7 gives you 7?
1.
7 to the first power. Yay. 7 to the first power equals 7. This one's a little bit tricky, so I'll help you out on this one. Unless somebody at home wants to jump on this one. What power of 8 gives me 1 over 8? It'd be -1. And let's see if we can't follow the logic here. Remember, you always start out with the base to this power equals this. So 8 to the negative 1 equals 1 over 8. Oh yeah, that kind of makes sense, right? Because if you have a negative exponent, what we learned when we worked with exponents is that you take the reciprocal and get rid of the negative from the exponent. So perfect. How about this one? Log base 6 of 1 over 36. I'll give you a little hint here. 36 is 6 squared. Does that help? Does? Good. So what should I put here, Katie?
-2.
-2. Nice. Because 6 to the -2 is 1 over 36. That'd be 1 over 6 squared, and 6 squared is 36. So excellent. Who remembers this kind of stuff? What power of 7 would give me the square root of 7?
Is it 1/2?
Oh, well done. Yeah, 1/2. Because 7 to the 1/2 power is the same thing as the square root of 7. Yeah, excellent, excellent. So let's continue. These are getting, these were getting harder, but now they're going to get easier. What power of 10 gives you 10? Well, we've kind of already been through that, right? What power of 7 gives you 7? What power of 10 gives you 10? The answer is 1. And of course, 10 to the first power equals 10. The nice thing here is now that we're down to log base 10 of all these numbers, if we don't want to think, we don't have to, because log base 10 is built into your calculator. So let's play around with it there. So I'm going to exit this and then clear it out, clear this out. So that's your log key. And if you take a look above it to the left, you see 10 to the x. And what I like to tell people is that it's kind of a reminder that this log key is really log base 10. Log base 10 of 100, well, really that's what power of 10 gives me 100. And, oh yeah, 2, that makes sense. And we can keep going. What power of 10 gives me 1,000? 3. And can you see kind of a shortcut for log base 10 of these numbers? What's the shortcut? Other than just plugging in your calculator.
You count the zeros.
Count the zeros. 4 zeros, that's 10 to the 4th power. Beautiful. Excellent. How about this one? Log base 10 of 0.01. Now, if you're looking at that going, I don't know, there's good news. You don't have to be a mental calculator in order to get that. You can just type it in, right? That's log base 10. Log base 10 is kind of like the default, just like square roots. When we're dealing with square roots, if there's nothing written in front of the radical, then, like right here, then it's understood to be a square root, not a cube root or a fourth root. It's a square root. That's the default. So you don't write the 2 there. In a similar way, I could write this as just, log of 0.001, because the 10 is understood to be there. You don't have to write it. It's the default. This is called the common logarithm, as opposed to what we're going to work with in the next section, which is the natural logarithm. All right, does anyone get these values? Log base 10 of 0.01 should have been -2. Log base 10 of 0.001 would be -3. For a little bit of practice here, what would be the equivalent statement using exponents for that last one there? Always start with the base. The base to this power equals that. So that would be 10 to the -3rd power equals 0.001. And if that doesn't quite look right to you, well, let me demonstrate that it is actually going to work out. That's 1 over 10 cubed. And 1 over 10 cubed equals 1 over 1,000, which is the same thing as 1/1,000. So it works. Nice. All right. Now we practice a lot going from logarithms to exponential forms. You could also be given this in another form. We could be asked to go from exponentials to logs. So, you know, going that direction, I would keep in mind what's at the top of your handout. And that is this stuff up here. A to the y equals x. That's equivalent to log base A of x equals y. So let's see if we can't just rewrite that for ourselves. It's going to be A to the y equals x, and log base A of x equals y. And there's no shame, there's nothing wrong. In fact, it's a good test-taking strategy to write stuff down on your test. So if you wanted to write this down as soon as you got your test, right on it, hey, I got no issues with that. I actually kind of like that. So I think that's a smart test-taking strategy. It's called a memory dump. So things that you think you're going to need and might forget, just write it down. So what's this going to be? Log, what's the base? Now that base is written a little bit below the line with the logarithm. Log base, well, 10 of the y value, excuse me, of the x value. X is over here. So log base 10 of 1,000 should be 3. So there's your base, there's your A, there's your x, and a 3, that's your y. So it's just a matter of rewriting these things in an equivalent form. And you can check that pretty easily on your calculator, right? Log base 10 of 1,000? Yeah, that's 3. How about the next one? Let's take a look here. Log. What base am I going to use? 3. Good. The base is always going to be this term here that has the exponent associated with it. That's always going to be your base when you're going from these exponentials to logarithms. So log base 3 of something equals something. Let me catch up with my loyal followers on the chat. So, all done. Thank you. See ya. Log base 3 of 1 over 81 equals the exponent, which is -4. Now that one's a little harder to check until we learn a little bit more about our calculators and perhaps a particular formula in the next section. Now if you want to test yourself, maybe pause the video for a moment and see if you can't figure out these next 3. But I guarantee you there'll be test problems like this. And this is just kind of a good basic, all right, here you go. I want you to know this. Do you know it? That's all there is to it. I'm not trying to trick you, but there's going to be stuff like this. Go from exponential form to logarithmic form. All right. So let's take a look at the first one. The base is going to be m, so log base m of p equals m. The one below that, again, that's your base, log base b of 2/3 equals r. And the last one we can actually check if we wanted to. Log base what? Log base 4 of 8 equals 3/2. Nice, nice. Now, before I move on, are you starting to get comfortable going back and forth between exponentials and logarithms? And the big thing to realize is that the logarithm is just the inverse of an exponential. It undoes what the exponential function does. So if I were to take the log base 4 of both sides of this, log base 4 of 4 to the third power would just be 3. It'd just be the exponent. So we'll practice with that some more. You know, probably have to follow it now. But what I want to apply that to is some graphs. I'm going to start by looking at the graph of log base 2 of x equals y. Except, boy, graphing this as it stands is kind of difficult, because either you're going to have to do some calculations that'll make you uncomfortable, or you have to be extremely clever choosing points. And rather than being extremely clever, I'm going to be clever in a different way. I'm going to rewrite this equivalently using exponents. So what would this be if I wrote it using exponents? What would the equation be?
2 to the y equals x.
Beautiful. 2 to the y equals x. And unlike a lot of the equations that we deal with, the difference here is that you've got x solved for and not y solved for. But that's okay. As long as you can get pairs of points out of this relationship, that's fine. So here's what we're going to do. We're going to set up a little t-table down here, x and y. But instead of plugging in values for x and getting values for y, we're going to plug in values for y and get values for x. So I'm going to plug in -2, -1, 0, 1, and 2. I'm going to plug in those values for y. And remember, this is for 2 to the y equals x. So when I plug in those values for y, I get values for x. We're going to start from the bottom up. 2 to the second would be what? 2 to the second would be 4. If I plug in a y equal 1, I get 2 to the first, which is just 2. How about 2 to the 0? Two to the 0 is 1. 2 to the -1 is 1 over 2. And 2 to the -2 is 1 over 2 squared, which is 1 over 4. So there you go. Without having to be terribly clever at all, we got a nice set of points. And now we're going to graph these things. Let's pay attention to the units on the x-axis. They're in units of 2, so each vertical line here represents a distance of 2 between it and the next vertical line. So the first one is 1/4 and -2. So I have to kind of be pretty good about graphing that one. So this is going to be the point 1, 0, and I'll put that on my graph because I notice that it is a point that I'm going to graph. But if that's a 1, that's a half, and then 1/4 is about right here. 1/4 and -2. So right down there. And then 1/2 and -1. Well, that's going to be about here. So I'm graphing some of these early ones. 1/4, -2, 1/2, -1, 1, 0, 2, and 1. So 2 for x, 1 for y. And then the next one I get is 4 for x and 2 for y. And I'll throw in a bonus one for you, 8 and 3. So 8 for x and 3 for y. That'd be out here. So yay. Let's look at all those. And let me try and play a college-educated version of connect the dots. So it looks something like this. And there's your graph of y equals 2 to the x. It's quite possible that I could ask you to graph this or something like this on an exam. Now, it's true that you've got Desmos to use. Desmos makes this pretty easy, but I still would like you to know and understand how we got this graph. So let's maybe repeat this with a similar function on a different base. You can either use 2 or 4, 4 or 3, doesn't matter to me. So the next one I want to graph, we'll do 4. We'll do the graph of y equals log base 4 of x. Now, if I asked you to do this on an exam and actually plot points, here's roughly what I would expect. I would expect you to rewrite this using exponents. So let's start there. See if you can't rewrite this using exponents. Now I realize that maybe I've written this a little bit differently than I have some of the other ones. Usually we have log base 4 of x equals y, that is we have a log on this side. But it's still the same. You should be able to rewrite this as an equivalent expression using x equals something. And let's see, I might have an answer to that in my chat. No, not yet. Okay. Well, let me help out here. That's going to be 4 to the y power equals x. And then what I would do is I would try and plot some points. Let me put a little t-table up over here, because I know my graph's not going to come over here. X and y. -2, -1, 0, 1, and 2. That's all that we're going to have room for. Remember, you're putting in values for y. So 4 to the 2 power, 4 squared is 16. 4 to the 1 power is 4. 4 to the 0 power is 1. We could fill in our graph. I might not graph the top point. See if you can't fill in these last 2 here for me. That'd be 4 to the -1, which is 1/4. And 4 to the -2, 1 over 4 squared is 1/16. That one's going to be really tough to graph if you're going to try and graph it very accurately. So I'm just going to focus on these 4 right here. So again, we've got a point at 1 and 0 that's on our graph. And at -1, excuse me, at 1/4, we're at -1. So 1/2, 1/4, about there. Like I said, trying to graph 1/16, I mean, that's going to be ridiculously close to the y-axis, something like that. I wouldn't expect that. From there, it goes up to 4 and 1. That's going to be out here. And then way out to 16. Boy, you got to go all the way out to 16 before this function goes up to even get up to 2. And kind of what that's saying is that the logarithm is a very slow growing function. If you ever get into computer science, a lot of times you like your search algorithms to have what's called search of log of n. That's awesome. So the time it takes you to do bigger and bigger searches increases with the logarithm of the search size. In other words, it doesn't grow exponentially fast. Grows up logarithmically. Y equals log base 4 of x. Beautiful. Now there's a few things we should pick up from this. And unless there's some questions on this, I'm going to go to decimals and start talking about those things in decimals. I'm just going to open up a new decimals page here. So I'll start by looking at y equals log, let's see what, on log base 2 of 4, or 2 of x. So I found this just today. If you want log of a particular base, you're going to click the keypad, go to functions, and then, let's see, where is it? Yeah, here we go. Log base A. So it lets you put in the base. So you have to go down to the calculus menu underneath the functions menu. Log base 2 of x. And there's your graph. Now remember, log was the inverse of the exponential function. So y equals 2 to the x, that should be the inverse of that graph. What are those graphs going to look like when they're inverses of each other? You remember? What's the relationship there going to look like? When I click this button, what am I going to see? Is it predictable? Well, they are. In fact, let me give you a little help. Remember now? They're mirror images of each other around the line y equals x. So here's the line y equals x, and they're mirror images. You've got a point at 0, 1 on this graph. Your logarithmic functions are going to pass through 1, 0. Your exponential function gets close to but never touches the x-axis. And guess what? Your logarithm gets close to but never touches the y-axis. Now let's remind ourselves about domain and range. So the domain of our exponential function was everything, right? Great, it was everything. But the range started at 0 and went to infinity. So that's the x values, or that's the y values you got for our blue graph here. They come down to 0, never quite touch 0, but they go up to positive infinity. Now, when you go from exponential function to logarithmic function, from function to inverse, those things interchange. So the domain of this function is the range of the exponential. Oh, that's going to be 0 to infinity, not including 0, and that's important. And the range is going to be everything. It goes from negative infinity to infinity. All right, so let's see here. Let's test that a little bit. Now, I said that the domain of the logarithmic function is from 0 to infinity, but did that 0 get a parenthesis or a bracket? Can you take the log of 0? Well, let's find out. You don't have to trust your instructor because your calculator knows. You can't take the log of 0. It's just not defined. And when you look at the graph here, it kind of makes sense. It's going down, 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 getting closer and closer to the y-axis, but it never quite touches it. It's not defined at 0, just like the exponential function never quite gets down to 0. They're just inverses of each other. So the bottom line here is that the domain is 0 to infinity, and the range is negative infinity to infinity. It's just the reverse of what you get for the exponential function.
So y wouldn't be 1, it would be undefined?
What do you do?
Like when it's
The log of 1?
10 of 0?
Log 10 of 0 should be undefined because 0 is not in the domain. Remember, your domain
Oh, yeah. Okay.
main doesn't include 0.
Oh, yeah.
But if you do log of 0.0001, you should be okay. You'll get a very big negative number, but that's okay. So as you get closer and closer to 0 with the value that you're taking the log of, this function is going to dive deeper and deeper down towards negative infinity. So you're going to get bigger and bigger negative numbers as you take log of something closer to 0. So so log 0.0002, -3 something. What if I put in a few more zeros here? 0.0000036, and so on. So I'm getting bigger and bigger negative numbers, and eventually I can get as close to negative infinity as I want. Okay, let's play around a little bit with the graph of the log and see if we can't work our way through some of these examples. For instance, example A here is asking us, well, and I think in WebAssign they're going to give you the graph of all these different functions and just ask you match them up. So we're going to start with log base 2 already graphed. Let's see if we can't predict some of the shapes that we get when we look at some of these other things. So y equals log base 2 of x, and we're going to compare that to y equals negative log base 2 of x, and y equals negative log base 2 of negative x, and finally y equals log base 2 of negative x. So these three here, and let me write it down for you here. Let's see if we can't predict what kind of flips and shapes we're going to see here when we do these kinds of different translations. So I'll start with negative log base 2 of x. How is this going to look compared to this one?
Is it going to reflect over the x-axis?
Yep. So flipped around the x-axis. Excellent. Let's go down to this one. Someone else. Instead of a negative out front, what if I took the negative and put it inside, took the log of negative x? How's that one going to change compared to this one? What's that going to do to the graph? Last chance. Flipped around the y-axis. Let's see a couple of these things, because it's kind of hard to imagine sometimes. So here's the graph of y equals log of x. And then let me put a negative out in front here. And that's just going to flip the graph. So it started out as a graph in red. Now it reflects it around the x-axis. What if I took that negative and put it inside here? Well, now it's going to flip it around the y-axis. Okay, great. And then one more trick here, last one. What if I did both? Try and use your imagination to figure out, well, what's going to go on this time? And I'll kind of demonstrate it this way. Copy this here quick. Yeah, there we go. All right, so in this last example here, there's been two things that we've done. First thing we did, comparison to the red graph, is we flipped it around the x-axis. Okay. And then it's not enough just to flip it around the x-axis, we also flipped it around the y-axis. So that would be your ultimate shape. So if you wanted to look at beginning to end, there's your two graphs right there. So nice. Ooh, here's a good question. What's the domain and range of this one? Of this last one? And I'm just going to write flipped around both on my paper while I let you think on that. So it's kind of a nice follow-up to that one. Let's look at the domain and range. Is the domain everything? No, it doesn't look like it. So domain, we're looking at the x-axis. So y equals 0 is the x-axis. But this isn't defined for everything. It's just defined for x less than 0 right there. So that range of values on the x-axis starts from left to right, from negative infinity to infinity. Or so negative infinity to 0. I'm sorry. So negative infinity to 0. So that's going to be our domain. Negative infinity to 0. And our range. How about our range? Those are the y values. Yeah, it's harder to see here. The top y value should be pretty easy. It's hinting at it quite strongly that this goes up to positive infinity. It actually eventually will get down to negative infinity. Take the log of a big enough number, it'll get down to negative infinity. So the range will be everything. So negative infinity to infinity. Like that. So there's your domain and range. Now some of these are properties of logs that we're going to learn about in the next section. So let me save some of that till then. We'll come back there. But there is one that I want us to figure out. It says find the value of a in log base a of x equals y for the graph below. So, okay, this is a good one. So we've got y equals log base a of x. We need to figure out what a is. And the one thing that I want you to notice about this graph is that it passed through one point in particular, right? What was that point? It was like 2 and 1/3, right? 2 for x, 1/3 for y. So 2 and 1/3. So that's your x and that's your y. And what that means is we can plug that into this equation, and it should work. So that means 1/3 equals log base a of x, or log base a of 2, I should say. Now, maybe you're more comfortable thinking of this as log base a of 2 equals 1/3. I mean, personally for me that helps out a little bit. I don't know if it makes a difference for you. But my suggestion would be to start by rewriting it this using exponents. What would the equivalent expression be using exponents? See if you can't come up with that one. Write it using exponents. Remember, always start with the base to this power equals this. So that would be a to the 1/3 equals 2. And we still haven't solved for a, but we're at least a little bit closer. how could I solve for a in this case? Well, the trick that I tell my students typically is when you have something like this, something to a power, and you want to get rid of the power, you're going to raise both sides to the reciprocal of this number. What's the reciprocal of 1/3? Katie? 3. Yeah. So cube. And if I cube the left-hand side, I have to cube the right-hand side. But here's the nice thing. A number times its reciprocal, because remember these exponents are going to multiply, number times its reciprocal is 1. 2 cubed would be 8. Yay. And so really what this ends up being is that log base 8 is what we're working with. Y equals log base 8 of x. That's our function for this one. Yay. All right. So one last little bit here. It says the graph of the function, or it says graph the function not by plotting points, but by starting from the graphs in the figures below. And this one's kind of nice. They're showing you that e to the x and y equals ln of x are inverses of each other. And we'll talk more about ln of x coming up. Yeah, I probably could mention it now. And then you've got all these functions. Now, the bigger the base, the flatter the function. One thing I do want to point out is all of these pass through what point in particular on this graph? All 4 of these functions. Log base 2, log base 3, log base 5, log base 10. What do they all pass through? They pass through the point 1 and 0. That's going to be on the graph of log base A of any graph. As long as A is a legitimate base for a logarithmic function. The base has to be greater than 0 and different than 1. So let's do a couple shifting problems here. So f of x is going to be log base 5 of x minus 4. Now we don't necessarily have to have a perfect image of this graph in our mind. There it is. But if we looked at the graph, log base 5 of x minus 4 versus log base 5 of x, then one of these graphs has been shifted. This graph has been shifted relative to this graph. So the question is, well, how has that been shifted? Which direction? What is that minus 4 going to do to our graph? Shifts left, right, up, or down?
Right.
To the right. What do you think? Is she right? Good. Yeah, it's shifted to the right by 4. Right by 4. And it doesn't hurt to look at that. So let's take kind of a quick look at that. Let me shut that graph off. I'll just turn this one on. Make that base 5. And then I want that again, except minus 4. So here's our graph. And then here's our graph, again, shifted to the right by 4. And you can see that this point is at 1, 0. This point should be at 5, 0. Perfect. Shifted to the right by 4. But there's something else that's been shifted to the right by 4. And that is our vertical asymptote. Our vertical asymptote was at x equals 0. It was this value right here. Where's the vertical asymptote in our new graph? What value of x? 4. It's got shifted to the right by 4. So let me put that in orange here. There. that's going to change your domain and range. Well, it's going to change your domain. Your domain is no longer 0 to infinity. What is the domain here now? Let's see. Our domain is going to be 4 to infinity. And in fact, x equal 4 is going to be a vertical asymptote. Nice. Nice. Okay, let's keep going. The range is still going to be everything. So the range of this function is going to be negative infinity to infinity. Nice. So, not that I'm mean or anything like that, but on a test, what I could do is I could give you log base a of x minus 4. And then you can't exactly do this with decimals or your graphing calculator because you won't have a base to plug in there. But you should still be able to figure out that, okay, that's been shifted to the right by 4. It's going to have a vertical asymptote at 4, that kind of thing. So I'm encouraging you to understand the shifts in these graphs. Now, I kind of wanted to hold off until the next section on this, but I guess I'll share it with you now because it appears as though we need it in this section. So just some notation. Log base 10 of x is the same as log of x. You don't have to write the base 10. It's just understood to be there. Like square roots, and I think I mentioned that before tonight. But there's another one, log base e of x. I'll actually write it as log base e quite a lot because I think it's less abstract. But WebAssign and textbooks, anything, you'll never see log base e of x. It's always going to be written as ln of x. I mean, it's great. It's the natural log versus the common log. The common log sounds a little degrading. It's like, oh, it's just a common log. But I don't know, that's what it's called, the common log versus the natural log. The natural log, base e comes up a lot. It really does. And it does come up in this last one here. So let me show you the graph of ln of x. And really it's the graph of log base e of x. Y equals ln of x. So it's just another typical log function, not much different than log base 2 of x or log base 5 of x. They're all the same kind of graph passing through 1, 0. But what's the log of, let's see, what was the last one here? Nope, this one. Yeah, ln of x plus 5. So let's take a look at that one. Maybe we can make some predictions first. ln of x plus 5. Before I type in that 5, see if you can't figure out what the graph of that's going to look like. So we're going to have f of x equals ln of x versus g of x is ln of x plus 5. So what's this graph going to look like? How is that going to get shifted? All right. I think I see to the left by 5. Perfect. Thank you so much. That coming through our chat. So left by 5. Let's see if we can't figure out the domain and range and asymptote as well. So coming back to our graph, ln of x plus 5, and let's zoom things in along the x-axis a little bit. So the point that was at 1, 0 right here is now at the point negative 4 and 0. We did have the x-axis as an asymptote for our old function right here, the green one. Let me get rid of this one. That was an asymptote for our green function. The asymptote for our new function is going to be x equals -5. So we can shut off this stuff here and here. X equals -5, that's our vertical asymptote. So our vertical asymptote x equals -5. There's really a couple ways you can come up with the domain. One is that we've looked at it, but the other one is you want to make sure that when you're working with a logarithm that x plus 5 or whatever the argument of this is, you want that to be greater than 0, which means x is greater than -5. So that's your domain. In interval notation, it would be -5 to infinity. And the range, as typical with all these things, or most of them, is going to be -infinity to infinity. Whew. Well done. Yes, good job. Okay. I think that does it for this section. Yeah, nailed everything there. Questions or thoughts before I end this one? Okay, let's stop things here.